Hi all. In this video, I want to talk about different distances in function spaces and specifically their relationships. Now, this is quite an advanced topic, but it allows us to expand more and see more examples about pointwise convergence, uniform convergence, and by having a third notion of distance, we really start to appreciate how being careful about convergence is important. So let's consider the space of functions, and let's make them all continuous. If we don't make them continuous, we'd have to worry about some of these things being defined. So we define two metrics, d1, f, which is you take the absolute value of f minus g. Now this is always non-negative, and you integrate it from 0, 1. This is also a continuous function, so this integral is defined. And then we have the familiar metric of uniform convergence here. Okay, so now these are all metrics. Each of them has their own issues to check. There is another video, I think, where I discuss parts of this, but so in D infinity, the triangle inequality is a bit tricky. For D1, the equality 0 case is a bit tricky. And whenever you have two or more notions of anything in math or in applications, what you should ask yourself is what are their relationships? This was exactly the type of question that you were asked in the exam. You have concepts, what are their relationships? Particular here, we have kind of three things. Now, if you have an fn are a sequence of functions in x, so continuous functions, and f is in x, then there are three statements, and we'd like to know what is their relationship. So limit n goes to infinity of fn equals f in d1. So in that distance, we have the uniform distance, so the uniform convergence. This is equivalent by theorem from Wednesday that fn converges uniformly to f. And then we have a third notion, fn goes to f pointwise. So the question is, we have three notions. When are they the same? When are they not the same? Now, it's hard to give theorems that exactly capture when they are the same, but it's useful to begin to understand the differences through a series of examples. And this helps us understand what we can do. So one thing is that we always have an inequality in these distances. The d1 distance is less than or equal to the L infinity distance. And why is this? Well, for all x, we have f of x, and this is in the interval 0, 1, minus g of x is at most supremum over x. This is kind of like your homework problem. You've seen this. So the supremum, technically you should have a different variable here, and this is d infinity f of g. This is true for all x. So if you integrate the left-hand side, or integrate both sides, then you get that the integral of fx minus gx, which is equal to the d1 distance, this is at most the integral of d infinity fg from 0 to 1, but this is a constant. So what we are using here is the fact from 131a, that function less than another function has integral smaller than that. Now this is a constant integrated from 0 to 1, so you just get the constant. Okay, so we have the d1 distance is less than the d infinity distance. Now what this means that there is a relationship between these concepts. Well, the distances, whenever you have an inequality between distances, you have to get a relationship between convergence. Indeed, what you get is that if you have limit as n goes to infinity of fn is equal to f in the uniform distance, then they converge in the distance d1. This is a good exercise in using properties. It's similar to the question in your first homework that if you have an open set in the d infinity in the d1 metric, then it's open in the d infinity metric, or the one of these directions. So, yeah. So open in D1 means open in D infinity. But this statement, I mean, what it essentially hinges on is that, well, if you know that you get by the inequality from the distances, you know that limit as n goes to infinity, well, if you have that the first converges, you know that the distance in the one metric of them between goes to 0, but this is bounded above. Technically, this involves squeeze theorem by the infinity distance between f and f. But this infinity distance there is squeezed between 0 and 0, so it has to be 0. It's a sketch. It's not a proof. So if the infinity distance is small, then D1 distance is small. And that means that there is an implication between them. So we do get a relationship here that this implies the second. Okay, let's look at an example then. So other implications there do not really hold the same. I mean, we had, so we just said this one. This one is true from Wednesday. Uniform convergence implies pointwise convergence, but anything else is hard. You cannot, uniform implies D1. And that's what we said just. Uniform implies pointwise. So this is the strongest notion in a sense, because it implies the other ones. But between D1 and then pointwise convergence, their relationship is not quite clear. And we'll see one example that explicates that. So one good example is that we look at the function 1 minus x to the n. So this is this familiar function from lectures. These functions look like that. But this time, our limit function is a little bit different from the lectures. It's the constant function 0. G is equal to 0. So previously we defined this with the jump there. Now we don't include the jump. And what this means is that why we do this is that we actually want these functions to be continuous. So this is x, this is x. So then f does not converge to G either uniformly or pointwise. Well, it doesn't converge pointwise because uniform implies pointwise, and if you look at limit n goes to infinity of f n of 0, then that's 1, but that's not equal to G of 0, which is 0 in this case. So if you want the pointwise convergence, you really have to put the point there. Even then, you don't get uniform convergence. Okay, so it's not converging pointwise or uniformly. However, it is converging in the D1 metric. Well, and this is a computation. If you want to look at the distance between fn and g, this is the distance between fn and the 0 function. And well, what this means is that fn converges to g in D1. So in some sense, it still is converging. And what is this sense before we prove it? Fn, the distance D1, what it's measuring is the integral between them, which is measuring the area. D1 area between graphs. And in this picture, we see that the distance is going to 0, but let's be a little bit more rigorous. Let's just compute this limit. It's not a very hard interval. So this is equal to limit integral from 0 to 1 of fn x minus 0 dx. The formula for the function gives us integral from 0 to 1 of 1 minus x to the n dx. I hope you are able to integrate this. This gives us substitution from 0 to 1 1 over n plus 1, 1 minus x to the n plus 1, and there will be a minus from using a substitution there. And what we're left with is at 1 you get 0, and 0 you get minus, so 1 over n plus 1. So this is the same as the limit of this, which is the same as the limit of 1 over n plus 1, which is 0. We are done. So in this case, the distances can be computed, and they represent the geometric fact that the areas are going to 0. So in some sense, their graphs are still converging in that the difference in area between them is going to 0. But this is different than saying that the graphs have to converge, because they can have these sharp spikes that we exhibit here in this example. But there is another way in which these relationships can be tricky, and this is a particularly important example, and I want to highlight it. And this is the final example from this lecture, is that suppose you have this kind of a steep, previously we had a peak that kind of became sharper and sharper, but there's another way to have a weird peak, a peak that disappears, is you have a peak that's a hat, and you make this peak become smaller. So it becomes possibly taller at every step, but it's somehow in the limit, it's getting shifted over to the left and disappears. So let's look how this is defined. This is defined as a linear function, and linear function. So first, after a certain time, 0, 1 over n, you're 0, and at 0, you're 0. And between them, you have this steeple. That means first you're growing linearly with a big slope. And if you want to reach the value square root n in time 1 over 2n, then the slope has to be n to the 3/2 times 2. And then you want to come down from there to ensure that the boundary values are the same, continuous. So you have to start from square root n, and you have to go with the same slope down, but starting from 1 over 2n. The picture is much more suggestive, but the blue one is drawing this blue arc, the red part is drawing the red part, and the green part is drawing the green part, as you can verify after some thought. This is a particularly important type of example. It works for many things. Actually, all of the examples I've mentioned, they work for many things. So it's good to keep in mind, also in terms of your next exam. But so Fn are big somewhere. So they're not going to 0 in any sense. I mean, they're very big somewhere, square root of n. The maximum of the functions actually square root of n, and they're going off to infinity. But, and quite clearly because of that, Fn can't converge uniformly. This requires a statement proof, but it follows. And finally, but still, Fn does converge pointwise to g of x is equal to 0. Why is that? Because if you fix a value here, eventually it will be 0. And if you're at 0, you're always 0. So limit as n goes to Fn of x is equal to 0 for all x fixed. And moreover, you converge in the D1 metric because, well, if you look at to g equals 0, because if you look at the distance between Fn and 0, what is this? This is integral from 0 to 1 of Fn of x. And this one, okay, you could do the piecewise definition. It's the area of this triangle. What is the area? The base is width 1 over n. So it's 1/2 the base times the height, which is square root of n. So this is 1 over 2 square root of n. So therefore, limit as n goes to infinity of d1 of Fn to 0 is equal to limit as n goes to infinity of 1 over 2 square root of n, which goes to 0. So it converges pointwise, it converges in D1. But it does not converge uniformly. And it has this weird property that it's becoming very large in some parts of the space, but The D1 metric kind of doesn't care because it's coming very large in a very small area. So now the final thing is that you can modify this example a little bit. If you change the square root 2, so if you modify this, square root n to n, then the picture again changes a little bit. Okay, you still have pointwise convergence to this zero function, no uniform convergence for the same reason as above, but Fn doesn't even converge in D1. So the reason is that this time the area is distance between Fn and 0 is equal to the area is equal to 1 over 2n times n is equal to 1/2. And this is problematic. The distance is 1/2. It's not going to 0. And therefore, it's not converging in D1. That's the last example that I have here. So be careful when you're talking about convergence of functions, because we have, not only do we have different notions, we have different distances, and the relationships are not completely obvious. There are only two obvious relationships, d infinity to d1 and d infinity to pointwise. And this is the reason why, one of the reasons why we use d infinity so much is that it's the strongest notion and there are the strongest theorems hold for that. Often these theorems fail for these weaker notions, but you'd have to case by case evaluate every one of these statements.